Hi guys, welcome back to the physics closet. Today we've got a very special treat. I was going through it last week and I discovered this classroom set of CDL based computing systems, and one of them happened to be a Geiger counter. Now before we actually start this experiment, I want to go over how the Geiger counter works. Now this piece of equipment uses something we would call a Geiger-Müller tube, and this is a tube under a vacuum with a slight back charge of gas in it, meaning that there is still gas atoms inside, but it's under a reduced pressure from the atmosphere. Now this GM tube, Geiger-Müller tube, was first invented in 1928 and was used to detect radiation. How it works is we've got ourselves a little window up front, often ceramic or plastic. Most commonly in pancake detectors, it's a very, very thin film of plastic that's permeable to alpha radiation, so you can actually read accurately the level of alpha radiation. So we've got our thin window here, and here's the walls of our Geiger-Müller tube. Now inside this tube is a very, very thin piece of tungsten wire that runs down the length of it. Now it's insulated on both sides, so the outside of this tube would be a negative voltage, and the inside of this tube would be a high voltage positive. Now this very thin lead is hooked up to our little transformer here. And we have our little 9-volt battery going in. I'm not sure how well you can see these diagrams. Let's see, does it pick it up okay? I believe it does. There. So we've got our little 9-volt battery here and our leads going into it. Such. Now, regularly there's so little amount of gas in here that the voltage can't jump from this tungsten wire right to the outside. There's still too much resistance. But what happens is when an alpha, beta, or gamma particle flies into this tube, it ionizes the air. That's why this form of radiation, these forms are called ionizing radiation. An ionized gas is very conductive. So when this particle actually flies into the tube, it bridges the gap, and for a split second, the electricity can cross. And that's why you hear it tick when a particle flies through. I really can't snap with these gloves, but you understand the point. That's why when you turn it on, you hear a tick. That's a particle actually flying through the window and bridging that gap for a millionth of a second. Now, as soon as that particle's gone through the tube and either exited or lost its energy, the ionizing stops, and the tube resets back to its original values, and the tube recharges, and for a couple seconds it might be blank, and another particle will fly through and you hear another tick, which is why these tubes give their classic tick when put into an audible mode. Now I can actually bring this over, and you can get an idea from how far away I can actually begin to detect the radiation that's inside our little box here. Now for the experiment that I want to try today, I want to actually see if it's possible, using paper and aluminum, to filter off the types of radiation this Cesium-137 isotope generator will actually be giving off. When I say Cesium-137, I mean mostly Cesium-137 with minimal amounts of barium-137M. Being that its half-life is only about 2.5 minutes, there won't be too much barium in here at any given time. Now, first things first, take out our isotope generator, and we'll just get a ballpark number of what this thing overall will emit. So we'll turn our Geiger counter on, and it right now on the gauge setting and clicks per minute is on the ×10 setting. And we'll bring our isotope generator right up against the window. And we'll sit here and we'll let it normalize for a minute or two. To be about 180 clicks per minute times 10, so it's about 1,080 clicks a minute. just about 1,080 clicks a minute overall. Mind you, it's on the times 10 setting, so if this is 180, it would actually be 1,080. I'm sorry, correction, 1,800, 1,800. So we've got about 1,800 clicks a minute overall from our cesium source. I'll turn this off to stop pestering us. So our first step will be to use actually this piece of paper here, because I know alpha radiation cannot penetrate this cellulose-based paper. So with that, we'll continue our experiment now using this paper as a block in between our emitter here and our Geiger counter, our detector. See if I can get a good line up here. It looks to be right back where we started, about 1,080 average, which is interesting. Now what that just told me right there is cesium-137 and barium-137M, both of those isotopes must be little to no alpha generation amongst them, which is an interesting thing because a lot of the radiation that we see is alpha. In U-235, for instance, or U-238, most of that radiation generation is alpha. Now, what we can do is we've got ourselves an aluminum window. When I say window, it's a window, but only to certain types of radiation. This is a window to, say, gamma radiation, but it's not a window to beta or to alpha. Now, knowing that there is no alpha, we can logically assume, we've got our A here, stands for alpha, there's nothing. Now what about our beta or our gamma? Well, if I can filter off all of the beta and leave us with just the gamma, we've got our overall here between the two. I could subtract the amount of gamma from our overall to get our beta. Now I will have both of our unknowns here, beta and gamma, and I'll have them in clicks per minute. So I will take our isotope generator here with our open end facing out. I'll place it in our generator. I should say I'll place it in our window. I'll bring our counter up to it. We look to be about 1,030. Correction, 1,300. I keep messing that up. About 130, which would be about we'll call it 1,300 is our known gamma. So if we're 1,300 subtracted from our 1,800, we can logically assume got about 500 clicks a minute. Interesting, interesting. Interesting to know this is largely a gamma emitter. Now this is funny because gamma emission is known to penetrate very, very long distances, but because there's so little cesium here, originally, way back in 2001, August of 2001, there was 9 microcuries of cesium. Now, it's about to its quarter life right about now in the sense that a quarter of the original material is gone. It's very interesting to see this high level of gamma radiation, but at the same time, so low energy that it's very difficult to detect at range until you get a little bit closer. So it's about 4.5 inches maybe is when you really begin to detect this stuff. It's still detectable at 5, but it's not too awful much above background at 5 inches. So it's very interesting to see such low-level gamma radiation, whereas in nuclear reactors where the energy of this gamma is so much higher, it might take up to 14 feet of concrete to stop a gamma wave. Very interesting things to see. The original point of this little isotope generator was you pass an eluting fluid through here. It's some kind of a weak acid. I don't remember particularly what. I could go test for it come Tuesday. But we've got this eluting solution that would be poured through here, and that would completely wipe all of the barium-137M onto these little aluminum discs here. And since that barium-137M only has a half-life of somewhere around the ballpark of about 2.5 minutes, I think it's 2.54 minutes, we could actually take this Geiger counter and watch the radioactive gamma decay of this barium-137 begin to fall off. And that would prove that there is such thing as radioactive decay. But being that I don't have the eluting fluid, it's pretty much useless to me right now, other than being able to filter off the alpha, beta, gamma that I can currently see from the Cesium-137. This is a really cool kit. So far I've been able to find absolutely no natural occurring radiation other than background over the places that I've gone. I'm really excited to maybe go to a gravel quarry sometime within the next week and pick through. Maybe I could find some uranite or some form of low alpha, beta, gamma emitting natural occurring minerals. But we'll see about that. So guys, I hope you liked what you learned today. If you learned anything at all, and if you didn't, well, I hope you enjoyed at least what there was to do. If you guys have any questions and comments, please leave it down below.